Hello, Accelerated Chemistry students. This is Ms. Crisafulli, and this is your Chapter 16, Section 1 video notes all over properties of solutions. So let's start by talking about solution formation. So the compositions of the solvent and the solute determine whether or not a substance will dissolve. So there are three factors that affect how fast a substance will dissolve: agitation, temperature, and particle size of the solute. So let's talk about agitation first. So if the contents of the glass are stirred, the crystals dissolve more quickly. The dissolving process occurs at the surface of the sugar crystals in the case when we're making iced tea with sugar in it. Stirring speeds up the process because fresh solvent, the water, is continually brought in contact with the surface of the solute, which would be our sugar. Agitation, stirring or shaking, affects only the rate at which the solid solute dissolves. It does not influence the amount of solute that will dissolve. An insoluble substance remains undissolved regardless of how vigorously or for how long the solute and solvent system is agitated. So basically, if something is soluble in your solvent, it will dissolve. If it's not, no matter how much you stir it, shake it, agitate the particles, they're not going to dissolve. Temperature is the second one. Temperature also influences the rate at which a solute dissolves. Sugar dissolves much more rapidly in hot tea than in iced tea. At higher temperatures, the kinetic energy of the water molecules is greater than at lower temperatures, so the molecules move faster. The more rapid motion of the solvent molecules leads to an increase in the frequency of the force of collisions between the water molecules and the surface of the sugar crystals. And the last one is particle size. The rate at which a solute dissolves also depends upon the size of the solute particles. The smaller the particles in granulated sugar expose a much greater surface area when colliding with water molecules. The dissolving process is a surface phenomenon, so the more surface area the solute has, the faster the rate of dissolving will be. Now let's talk about solubility. What's happening in this figure? Well, in this figure, the particles move from the solid into the solution. Some dissolved particles move back from the solution back to the solid. Because these two processes occur at the same rate, no net change occurs in the overall system. Such a solution is said to be saturated. A saturated solution contains the maximum amount of solute for a given quantity of solvent at constant temperature and pressure. In a saturated solution, the state of dynamic equilibrium exists between the solution and any undissolved solute, provided that the temperature remains constant. The solubility of a substance is the amount of solute that dissolves in a given quantity of a solvent at a specified temperature and pressure to produce a saturated solution. The solubility is often expressed in grams of solute per grams of solvent. Sometimes the solubility of a gas is expressed as grams per liter of solution. A solution that contains less solute than a saturated solution at a given temperature and pressure is an unsaturated solution. If additional solute is added to an unsaturated solution, the solute will dissolve until the solution is then saturated. Some liquids, for example, water and ethanol, are infinitely soluble in each other. Two liquids are miscible if they dissolve in each other in all proportions. Liquids that are insoluble in each are immiscible. Oil and water would be an example of immiscible liquids. Liquids that are insoluble in each other are immiscible. Temperatures affect the solubility of solids, liquids, and gas solutes in a solvent. Both temperature and pressure affect the solubility of gaseous solutes. So let's look at temperature. The solubility of most solid substances increases when the temperature of the solvent increases. A supersaturated solution contains more solute than it can theoretically hold at a given temperature. The crystallization of a supersaturated solution can be initiated if a very small crystal, called a seed crystal, of solute is added. The rate at which excess solute deposits upon the surface of a seed crystal can be very rapid. So the solution before is clear. Before a seeded crystal is added, then the crystals begin to form immediately after the addition of the seed crystal, and then this excess solute crystallizes rapidly. This is the process that they use to make rock candy. The effective temperature on solubility of gases in liquid solvents is opposite than that of solids. The solubilities of most gases are greater in cold water than in hot water. Let's talk about pressure. Changes in pressure have little effect on the solubility of solids and liquids, but they strongly influence the solubility of gases. Gas solubility increases as the partial pressure of the gas above the solution increases. So carbonated beverages are a good example. So these drinks contain large amounts of CO2 dissolved in water, and the CO2 makes the liquid fizz in your mouth and on your tongue. The drinks are bottled under high pressure of CO2 gas, which forces large amounts of gas into the solution. When the container is open, the partial pressures of the CO2 above the liquid will decrease. So then immediately bubbles from the CO2 form in the liquid and escape from the open bottle. As the pressure of the gas above the liquid increases, the solubility of that gas increases. As the pressure of the gas decreases, the solubility of the gas will also decrease. This is why you need to refrigerate your pop in cold temperatures when it's completely sealed to make sure that the gas does not escape from the liquid. And that is the end to your Chapter 16, Section 1 video notes. And as always, all the information from these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition textbook, resources, CD, and pearsonchem.com. Thank you so much. Have a good night.